Good morning, welcome. We are at the Bioretention, What Has the SAM Studies Shown Us? And as a reminder, these presentations are being recorded. During the Q&A portions, they won't be recorded, but they are being recorded. And just to remind everybody to please silence your cell phones or turn them off. So today, we have a whole slew of presenters. We have three senior students at Gonzaga University, Bella Brzezinski, Nicole Chen, Leland O'Hanlon, and also presenting will be Brandi Lubliner, who is the SAM coordinator at the Department of Ecology. So the presentation today will cover objectives and findings where available for the SAM bioretention studies. So with that, I will turn it over to Brandi.
Hello, okay, so can you hear me? All right, in the back there? All right, good. I'm Brandi, and I work at Ecology, and I'm your SAM coordinator. SAM is the program that allows Phase 1 and Phase 2 Western Washington permittees to collaborate their funds, pool their funds, and select study topics and choose studies. And so what I'm gonna do today is a pretty high level flyover on what we're learning. I brought some materials for the projects that are actually all the way finished. We produce these single page fact sheets. But there's the website that I have for SAM. I had hoped to show you a video, but it is on the website. There's no Wi-Fi, and I didn't embed it. So I'm just going to generally talk about the 8 studies we have actively going on. Well, actually, some of them have finished for the SAM program. So these are the 10 studies that the stakeholder committee has approved for funding. 2 of them haven't quite started yet, the orifice and the mulch. But we are looking at, does bioretention perform how we expect it to perform hydrologically? Does it reduce toxicity to salmon? We already know that that's true, but how long does that last? We're adding some amendments. Does that improve water quality treatment or toxicity reduction? How does it sequester PCBs? And then basically, how could we build a protocol to rate basically bioretentions across the region and figure out which ones need to be maintained? So these are the scale, the scope of the studies that SAM has going on right now. I hope I don't have to go into this too much, but bioretention is an engineered facility, which means it's sized using a model to receive and treat a certain amount of flow, like runoff and volume, and then treat the runoff for water quality across the hydrograph. And then there's some targets. We want it to achieve at least basic treatment, and then bioretention is also able to provide enhanced treatment on the west side, metals treatment on the east side. But these are also, these are not model assumptions, but they're modeled qualities, and those are the things that we want to verify with these performance studies. Retrofit, I want to bring this up because we studied a number of retrofits in the SAM program, and retrofits are a situation where you have probably a built environment that you want to add some additional flow control or flow treatment, runoff treatment to. It doesn't Ecology offers grants, and we don't require the retrofit to be sized the same way for new and redevelopment. And so we're just trying to get some additional benefit wherever we can. And when we studied these retrofits, they weren't always exactly to the designs that new and redevelopment have for bioretention. And so that was part of the interesting findings for some of them. So what we're learning about bioretention. I have developed a couple communication products that I really want you guys to know about. I can't show you, unfortunately, today, but I have a video which has essentially 8 of the leads of the study talking about their studies. I didn't do any of these studies. I'm coordinating for these studies. So it's really neat because they're talking about their studies, what they looked at, why they looked at it, what we're finding. And it's a really nice video. It's produced by the Association of Washington Cities. And then we also have another communication coming up because we did spend so much money in SAM and time over the last 5 years looking at bioretention. It deserves a deeper dive, to convey, what we're learning. And so I've been working with the Association of Washington Cities to build a GIS story map on bioretention. It has about 6 or 7 tabs, and it's going to be a better dive into like green spaces, how communities accept and own and enjoy bioretention, basically the social science aspect, or what the water quality treatment studies are telling us. Some of the results are mixed. Or how is it working for toxicity, those sort of things. So that GIS story product is not on the website yet, but it will be soon, probably by the summer. This is what the website looks like. Probably can't read that. And there is the video. You can see it. This would have been the point where I showed it to you. But it's about 5 minutes long. And so knowing there might be something going wrong with the video, I have some slides. So bioretention, we have a couple different blend studies going on. What we have in the manual right now is a 60-40 mix, which is 60% sand, 40% compost. And Ecology actually started funding a lot of these studies at the turn, like in 2009. They started a bunch of projects with Redmond and Kitsap, and we started learning that the compost part of that default mix exports a lot of nutrients. And that could be a concern if there's a water body, within a quarter mile or so receiving that surface discharge. It could lead to, some algae blooms or stuff like that. So we wanted to basically look at ways to reduce the nutrient export out of bioretention. What we've learned about the mix is ongoing. We continue to study that particular mix as well as different blends. And we have a project with Western, it's at Western. It's with, who's it with? Curtis Hinman's helping run it, and it's King County's leading the project right now to look at the different blends. So we've learned that in general, that compost layer and the sand combined does a pretty good job of reducing organic constituents that would absorb to a particle. So they're getting really great treatment of PCBs, bacteria, PAHs, and other organics. Whatever organics we're studying, basically they absorb pretty well. We're getting mixed results for metals, and a lot of time that may depend on the sand itself, if there's metals in the sand. It may depend on the influent concentration. As you know, export treatment studies are very dependent on the influent concentration. So you can get really good removal if you actually have enough pollutant coming into your cell. And then what we have been learning over time is that they do export nitrogen and phosphorus, sometimes at statistically significant levels, but we're not terribly sure yet that these are environmentally relevant levels. So those are some more of the work that we're working on. Thanks to NOAA and U.S. Fish and Wildlife Service and WSU, we do know bioretention helps prevent acute toxicity to our most sensitive salmon in the region. And we're looking at how long that lasts. And also, one of the things with the blend study, although we don't hold the blends responsible for reducing toxicity, it's a fabulous, awesome perk. We'd like to know if the alternative blends also provide that perk, or at least don't add to toxicity that we find in the runoff. And WSU's continued to advance the science, I'd say, on what is it in stormwater that's killing these sensitive species of salmon, and that work's continuing to evolve. We do know that they've attempted to rebuild stormwater quality and kill the salmon, and they're not really able to kill it with just like a mixture of organics and metals, kill the salmon, that there's something unknown in there. And the most recent research out in press is related potentially to tires. One of the studies we're adding is, what we have ongoing is, can fungal amendments improve water quality treatment? and this would be of the basic default mix. We're adding the garden giant or wine cap mushroom. I have the Latin name if you really want it. These studies are taking place in Seattle at a DOT research facility, and this project's actually just extended. There was not enough storms with the February snows to continue that project, so we're extending into through this spring to hopefully get enough storms. And it's paired with the PCB study too. So, like I said before, no one BMP can do kind of everything, right? There's trade-offs, and if you really need to work on a nutrient solution at a particular site, this would be a really good approach as a first screen for the organics and metals potentially, but you may want to follow up with a different BMP or treatment train for the nutrients. So keep that in mind. The last thing basically that we're learning is about the social acceptance, maintenance, those sorts of things for bioretention. We're hearing that these are really dry places. Keep in mind 60% sand, that's going to drain. And there's a lot of wetland obligate plants getting planted and failing in the center of bioretention. And maintenance crews that typically are already retained for maintaining stormwater facilities don't really know haven't necessarily been trained on all these specialty plants. They want to just bring their mower. So simplifying the planting scheme, making it more maintainable and easy to repair. And signage works. People in the neighborhoods really like signage. They get a better sense of what's going on. They begin to feel like they own that. That's part of their contribution to the environment. And as I mentioned before with these retrofits, we've had different guidance in the manual through the years. Sometimes in the past we had guidance that up to 24 inches of soil might be really good to help control nutrients. Well, we've learned that's kind of the opposite now, so we don't have that guidance in there anymore. But a lot of the older facilities were built deeper, and that was one of the things we studied. With SAM was a facility with more soil, and it produced more nutrients. And then, as I said, the retrofits, we're just adding a little treatment where we can, and that's great. That is what we want to be doing. But sometimes you need to really look at the inlets to these things. The facility's there and it's ready to do its job, but the water couldn't really get in that often. So there's things to keep in mind when you're sizing things in a retrofit situation. And they scale well. We've looked at a number of really tiny ones and a number of really large ones, actually. They do seem to scale well for function. And the last slide I have is basically that there is a perceived overperformance, like they drain really well at first, and that's some folks maybe think that that's not how it's supposed to be. They should be perking through the soil slower, but the guidelines we have in the manual are for end of life, so they should be perking slowly through that soil at the end of their life, which we hope is about 35-something years out, not right away. We don't want them to be infiltrating that water super slowly at first. So that is something that we've noticed in these findings and working with these study leads. Okay, I'm going to end my show and hand it over to a couple students in Spokane that are also looking at bioretention.